Thomas Morstan. I'm the ETP Deputy Theme Champion for Energy Distribution Infrastructure. So we have at least 3 presenters here today for you. So first we're going to have Samuel Hayward from Edinburgh University talking about smart hybrid distribution transformers.
Hi, I'm Samuel Hayward, and this is the presentation for my PhD project focusing on, done with the University of Edinburgh, titled Coordinating Smart Hybrid Distribution Transformers to Support Local Clean Energy Systems. So to provide some background, the UK government have set targets for reducing CO2 emissions, and in order to achieve these targets, we're likely going to see greater implementation of renewable distributed generators and electric vehicles within distribution networks. However, distributed generators and electric vehicles can cause power quality issues such as voltage violations and harmonics. A potential solution to these issues are hybrid transformers, which might be able to mitigate these issues. So what are hybrid transformers? Hybrid transformers are a combination of conventional power transformers and power electronics. The inclusion of power electronics provides the transformer with additional capabilities such as adjustable voltage regulation, harmonic mitigation, and power factor improvement. This diagram here shows the common topologies of hybrid transformers, just all the different ways in which the power electronics can connect to the actual transformer. In terms of project goals, there are 4 main goals for this project. The first goal is to develop steady-state models of the hybrid transformers for simulation purposes. The second goal is to then develop control and coordination strategies for these hybrid transformer models. The third goal is to create an energy system design framework that can incorporate the hybrid transformer models and their different characteristics such as sizing, placement, and topology. And the fourth goal is to assess what value hybrid transformers can add to the national power system. This project has been done in collaboration with Ionate, who are a private company that are letting us use their hybrid transformer to characterize our steady-state models. Ionate's hybrid transformer uses magnetic control in order to achieve its control capabilities, which include plus or minus 10% RMS voltage for voltage regulation, plus or minus 0.85 power factor for power factor correction, harmonic mitigation, and independent phase voltage control. Shown here is the steady-state model of Ionate's hybrid transformer. It can be modeled as a combination of a 3-phase transformer, a series-connected voltage source, a shunt-connected voltage source, and an impedance. This voltage source model can then be converted into a power injection model shown here, where the series and shunt-connected voltage sources are instead replaced with power injections that are determined by the compensating voltage and the reactive power used for power factor correction. In terms of control, the control of the hybrid transformers can be simulated through the use of linear optimization. This little flowchart diagram here describes the sequential linear programming loop used to simulate this control. Sequential linear programming is being used as a means to minimize any inaccuracies that could arise due to the reliance of the linear approximation of the hybrid transformer model equations. The first step of this sequential linear programming loop is to perform an initial power flow simulation where the hybrid transformers are inactive. We then take the results of this power flow simulation and derive a linear model of the network from them. We then use this linear model of the network as part of the linear optimization method alongside initial point values for certain optimization variables. We can then take the results of this linear optimization and use it to perform an updated power flow simulation where the hybrid transformers are now active. We examine the results of this updated power flow simulation to determine whether or not it's actually feasible. In the event that the results are infeasible, we look to the optimization to see if its constraints can be adjusted. If so, we adjust certain constraints to be more restrictive and then rerun the optimization in hopes of achieving a feasible result. We keep rerunning this optimization until either a feasible result is obtained or until we're no longer able to update the optimization constraints. When a feasible result is achieved, we compare the objective value of that optimization iteration with the objective value of the previous optimization iteration to determine whether or not an optimum solution has been found. If an optimum solution has been found, the sequential linear programming loop ends. If an optimum isn't found, the sequential linear programming loop begins again for the next iteration. Shown here are some preliminary results of the sequential linear programming method. In these cases, the method is being used to control hybrid transformers in order to achieve voltage regulation to prevent network voltages from deviating from 1 per unit. Shown here are the results for the IEEE 4-bus network, where on the left we have the network without hybrid transformer compensation and on the right with compensation. One hybrid transformer model was present in this network. Here's the IEEE 13-bus network, where again there's one hybrid transformer model present, and you can see the voltage regulation has achieved its goal. And here the IEEE 34-bus network, where instead we have two hybrid transformer models that are being coordinated with one another to achieve voltage regulation, and again we can see it's been successful. All the modeling and simulation for this project is being done in Open, which is the open platform for energy networks. It's a collection of Python files and packages that allow the users to simulate power networks using the ZBus modeling method. Open is being used for this project as it's open source and therefore offers greater flexibility than other available simulation environments. So in terms of upcoming work for the near future, my first main goal is to update the optimization and sequential linear programming method to instead control the hybrid transformers in order to maximize distributed generation within networks. I'm then going to go on to test these updated methods to make sure they work as intended, and then collect results for a paper. Afterwards, I'll then go on to develop a method to determine the optimal locations for hybrid transformer models within networks. So, in summary, this project mainly focuses on the modeling and simulation of hybrid transformers. We're doing this in order to demonstrate whether or not hybrid transformers can actually allow for more distributed generation and electric vehicles within networks. And that will show whether or not hybrid transformers can help us reach our carbon emission reduction targets. And hopefully, if all the results of this project are positive, we can help encourage and accelerate the adoption of hybrid transformers into power systems and start beginning to produce results in regard to distributed generation, electric vehicles, and carbon emission targets. That's it for my presentation. Thank you for your time. Is there any questions?
So wait for the microphone to come to you with questions.
Hi. Is that okay? Okay. My question was, I know that you're going to find the optimum placement, but do you have an idea of how many of these you need? Are they at transmission level or distribution level? Is it like replacing every second transformer, or is it like much less than that? Or?
Right now we haven't looked at it at such a wide scale. That might come later in the project when we might do a wide scale simulation of the implementation of hybrid transformers. Right now we're just taking individual test networks, and whenever there's a transformer or available spot for a transformer, we put a hybrid transformer there and test to see the results. So for example, for the 34-bus network, there's the substation transformer, and there's also 2 spots where it has voltage regulators in the default model. So for my test for this one, I took the substation transformer, I took the 2 voltage regulator spots and replaced them with hybrid transformer models. That's cool with me.
All right, fantastic. Thanks very much again, Samuel.
No problem.
All right. So next up, we will have Agatha Williams-Kelly from the University of Edinburgh also, and she'll talk about virtual synchronous machine functionality of modular multi-level converters.
Start my timer so you can see it. Okay, yeah, so this is my project title, Virtual Synchronous Machine Control and Design Requirements in Voltage Source Converters. So I think I'll go through what those things actually mean in the first few slides and then go on to some results. So first, an MMC is a type of voltage source converter. I've kind of used the terms interchangeably, but the MMC is the most common one in high voltage direct current, which is what I focused on. HVDC is used normally to connect generation from really far away loads or asynchronous networks to each other. So if you want to connect two different countries, you're probably going to have to change it to DC in the middle. And more, like the first picture, it's used to connect far offshore wind. And for that reason, there's a lot of them being built. And they're really, really big. So the middle picture is what an onshore converter station will look like, and the end picture is what it looks like actually inside the building. So yeah, an MMC is a collection of switches and capacitors, and the capacitors are switched in and out depending on the voltage you want to produce. So you end up with a slightly stepped waveform that I've over-exaggerated in the figure. It's good enough a lot of the time, you don't even need a filter. Yeah, so as you can imagine, that's really quite flexible, and that allows us to do a lot of interesting things with the control. So that's why I'm focusing on this type of converter for virtual synchronous machines. So to explain a virtual synchronous machine, first I'll explain why we need it. Frequency stability is quite an important part of keeping the power network reliable. The frequency in the power network is more or less a measure of the balance of supply and demand. That means that it's almost always changing, and the energy system operator works constantly to maintain the balance. However, sometimes there's a fault, like a lightning strike, and that causes the balance to change faster, because that will increase the frequency, or it will make an overcurrent, which means that protection devices will disconnect things. It will disconnect generators, it will disconnect loads. When that happens, the frequency changes more, and then something else disconnects, and it can cascade, and that will cause a blackout. The energy system operator will work to stop that from happening. And the amount of time that they have to work to stop that from happening depends on how high the amount of inertia connected to the system in that moment is. So this figure has a blue line which represents a high inertia system, and a black line representing a low inertia system. And the idea is, at the bottom of that fault, when the frequency is at its lowest, the point is, at that point the system operator has done something to fix the problem, but they need that time. So in a high inertia system, the frequency is much lower at that point than it is in a low inertia system. Generators are where we get most of our inertia, and the generators with the most inertia are gas and coal and nuclear. The generators with no inertia or limited inertia are solar, wind, and other types of renewables. So as we add more renewables to the system, this becomes a bigger problem. And we're at the point now where quite often in the UK, the connected inertia at any given moment is past the threshold that National Grid consider acceptable. I don't know if anybody remembers, there was a really big power cut in August 2019, I think. All the trains in King's Cross stopped going places. And in their report, National Grid listed low system inertia as a contributor to that. So that's why we want virtual synchronous machines. These would be converters that their control mimics the behavior of a synchronous machine, so that we can reduce the problems of low inertia without actually having hydrocarbons connected. One of the ways of doing that is by having droop control. So the idea is, if the frequency falls because of a fault, like falls that far, then the power output of the converter would increase by that much. So what my project does is looks at, is it possible to use the high voltage direct current converters that we have everywhere, that we're building, to provide this kind of control? The main issue, I think you can imagine with that, or one of the main issues, is that there's no energy. Rotating mass in a synchronous machine, it's a big, heavy spinning thing. That's a lot of kinetic energy. And when they rotate, when they slow down, the current that they're injecting into the grid goes up. And so my project is looking at how do we get around that problem. So this is an example of an HVDC interconnector that I think Ofgem cancelled. But anyway, I stole their image. Sorry.
The idea is that it was going to be connected to the south coast of England, between the south coast of England and France. So in France and most of Europe, the network is interconnected together. It's a much bigger, much stronger network than we have. So the idea was, what if for that little increase in power, we drain the energy in the converter, we drain the energy out of its capacitors and the cables if we have to, because we know that France has promised to increase the transmission across the DC link. So I simulated that many, many times. Oh, sorry, so the good frequency has to go down and the active power has to go up. So what if the AC to DC conversion went up? Yeah, so this is some of the results from my simulation. Each little block in each of these results represents one test case. So along the x-axis, there's a frequency change from -1 Hertz to +1 Hertz, and along the y-axis, there's a set power, so that's the power that was being converted before the fault happened. So -1 per unit and 1 per unit, because it's bidirectional. And for each test case, I looked at whether the converter was going to run out of energy. I looked at whether the current through the converter was too high for the power electronics, and I looked at whether the voltage within the arms of the converter stayed within reasonable limits. And when you put that together, you can see that current actually was the bigger problem, not energy. So this is how I defined current being hit. If the current hit its limit if it went above 1500 amps, because I got it from a data sheet of a submodule. And to improve on that, I added an extra block into the converter controller. I called it the current optimization block. It's a pretty basic optimization problem. And what that does is it takes the current that was in the converter and sort of shifts it a bit. So we maintain our functionality, but we just shave the peak off. So you can see this diagram. The darker color is without the lighter color is without the optimization, and the darker color is with. So if our limit was 1500 amps, we've made this scenario acceptable where before it wasn't. And it's the same fault and the same type of simulation. So I did that a lot of times and got this result. So all of the lighter blue squares are situations where before the current limit was hit and now it's not. So the conclusions I think you can reach from that is there is a bit of voltage synchronous machine, virtual synchronous machine functionality in an MMC. Playing with the control will allow that to improve, and that if we build more, we should just put a bit of current headroom and probably a bit of energy storage to make that something that's more feasible in future. In the future, yeah. Thank you. Does anyone have questions?
Questions for Erica?
We can so I really like the optimization that you did just using the kind of existing MMCs. What do you think kind of the next steps are in terms of modelling that either on bigger systems or like future optimizations?
There's a few different directions that you could go in. I think one of the things I've been working on is also improving the voltage limits, because once you've done one, you keep going until you find the optimum. So I'm working on that, but I think another important part of this project that I haven't touched on is I'm saying, okay, I can produce this improvement or this increase in output power, but I haven't gone into, okay, what does that mean for the grid? So I think it needs to be defined more like that will have this effect on the frequency nadir.
Thank you very much. And thanks very much for your very interesting presentation. I'm Graham Burke from the University of Strathclyde. Are you aware of what any downside is? You know, what's the downside to that change if that's the upside?
Mm-hmm.
Is there anything that would prevent you just adopting that? Is it a cost factor? Is it a design? Are there design risks that are presented? Just wondered if you share some of those.
Well, the most obvious one is there's no financial incentive. The reason I went this way is because, from speaking to people in industry, it looks like there will be. But as it stands, there's absolutely no reason to do that from a financial point of view. Technically, that fast ramp isn't what, because the idea behind this was if you retrofitted, but that fast ramp of power isn't something HVDC in the past has been designed for, so theoretically possible, but you know, you're adding stresses to your system, so you, again, really need to be paid for that, I guess.
Okay, thank you.
Any other questions? All right, fantastic. Thanks. Thanks for All right. Yep. So next we'll have Charlie Shepherd from the University of Dundee talking about overhead line foundations. Thank you.
So good afternoon. My name is Charlie Shepherd, and I'm one of the PhD students funded through ETP and the industry sponsor SSEN. So today I'm going to give my presentation on the optimization and enhancement of the uplift response of overhead line foundations. So an outline of the presentation, the background of the project, issues with the current approaches adopted by industry, so those by SSEN, the scope of the research, 1G physical testing that I've carried out to date, the setup and results of that, and then on to initial finite element method, FEM simulations, the results and limitations of that, and then on to future work on steel grillage foundations and helical pile groups. So background, as we see an increase in renewable energy, in particular onshore and offshore wind, these are often generated in remote regions and require connection to the transmission network. However, the existing transmission network has insufficient capacity to carry this additional load required. So there is a need to develop new transmission infrastructure, such as the East Coast 400 kilovolt overhead line upgrade, and the foundations used for pylon structures are typically material-heavy concrete foundations. So as I mentioned, the current approach for foundations are these material-heavy concrete foundations. There are some issues with that. These include the high embodied CO2, the import of primary aggregates, which scars the landscape through their extraction, and there's an issue with the curing time, which leads to delays in the erection of the tower onto the foundations. The use of concrete foundations is more of an issue in challenging terrain, where there's no existing infrastructure to deliver the concrete, which requires the development of haul roads or through airlifting. So these temporary access routes are environmentally damaging, scarring the landscape. There's the additional costs involved in that, and in areas such as peatlands, when the peatlands are disturbed, this can release emissions through that as well. So the scope of the research, the industry sponsor is particularly interested in non-concrete foundation solutions. And two of the options we're looking into are steel grillage foundations and helical pile groups. These can be installed using low ground pressure vehicles, so either eliminating or mitigating the requirement for haul roads. So the scope is to develop an understanding of the uplift response of these two foundation types, optimize and enhance their performance, observe the resulting failure mechanisms which aren't well understood for grillage foundations and helical pile groups, which will then lead on to the development of analytical solutions for determining the uplift capacity and load displacement response. So testing to date has involved 1G physical testing. This is the model grillage setup that I've developed. So the aim is to investigate the optimum grill spacing and the influence of soil density. So the grillage model set up here is in plane strain conditions. I'll explain as to why we've done that in a bit. It was a reduced scale of 1 to 10, and it's capable of investigating the spacing ratios of a third, half, 1, 2, and 5, where S is the spacing between two individual grills, and W is the width of the grillage member, which is 20 millimeters for this setup. So the test setup itself, the grillages were wished in place, so not modeling the excavation and backfill influences at this stage, but this is something we're going to look into at a later stage. The grillages have an embedment depth to width ratio of 1, and the sand was prepared through hand stirring, giving a loose relative density of about 54%. So as I mentioned, it's a plane strain model, so it's a 1G plane strain uplift test. It is a static uplift test, and the reason for conducting the model in plane strain is so that PIV can be carried out alongside the testing in future, that we're able to observe the resulting failure mechanisms, which will inform us on the analytical solutions we develop for the uplift capacity. So the results of the 1G physical testing, we can observe, so the graph here shows a low displacement response that prototype scale. So the results have been scaled back up to full scale foundation. We're getting an uplift response for a solid plate about 800 kilonewtons. And we can observe that for spacing ratios of third, half, and 1, so where the drills are close spaced together, we're getting a comparable uplift response to a solid plate. We're also observing a reduction in stiffness as the spacing ratio increases, so we're getting a greater displacement for a given uplift resistance. This is important when considering the displacement criteria for overhead line foundations, which is a vertical displacement of 25 millimeters. As we can see, for the larger spacing ratios, we're not reaching the ultimate uplift capacity at this criteria for those two spacing ratios for the loose relative density. Oh, and also that for the spacing ratios of 2 and 5, we're starting to see a significant reduction in the ultimate uplift capacity. So in addition to the 1G physical testing, some numerical simulations were carried out to observe the development of the failure surface. So it was a similar setup to the 1G physical test. So it was in plane strain conditions, at a reduced model scale, and investigating the spacing ratios mentioned. So from the plot here, which is the shear strain, we're able to observe that as the grillage is uplifted, we're observing a sort of wedge failure, and this develops at the dilation angle of the sand. And that between the grills, we're starting to observe sort of arching of the soil. And on the slide here, we can observe that as the spacing ratio is increased, so it's sort of fewer grills within the grillage, greater arching is observed, and that it's altering the overall failure mechanism of the grillage. So as we had with the 1G physical test, a low displacement plot has been plotted for the numerical simulations, and from that we're getting a similar ultimate uplift capacity for a solid plate, and we're observing that similar reduction in stiffness. However, we're not observing the same reduction in ultimate capacity for the greater spacing ratio. So on this graph, we also have the 1G physical testing for a spacing ratio of 5. And if you can see it on the graph, for from the numerical simulations with a SW of 5, you can see no difference to a solid plate. This is due to the continuum nature of FEM, where the soil flow mechanisms are not captured. Oh, sorry. And this is why, as I mentioned, we're interested in looking at PIV. This is so that we're able to observe the failure mechanism in the 1G physical testing. So on to future testing now. For the grillages, as I mentioned, we'll be conducting PIV, investigating the influences of backfill density, so in medium dense and dense soils also, simulating the excavation and backfill so that the model isn't wished in place, so sort of investigating the influence you'll experience in the field from digging and excavation, placing the grillage and backfilling, and then also looking at means to enhance the capacity further through geosynthetic reinforcements such as geocells and geogrids. And on the helical pile groups, this will first involve establishing a procedure for installing helical pile groups on the geotechnical centrifuge before investigating the influences of pile-to-pile spacing, so how closely the piles are to one another, and the influences of installation disturbance on the installation requirements through such as the torque involved in screwing the pile into the ground and the capacity of the pile group. And then also means of enhancing the uplift capacity further through altering the advancement ratio, which is the speed at which the screw pile is screwed into the ground relative to the helix pile pitch. So that's the end of my presentation today. So thank you for listening. If anyone has any questions, I'll be glad to take them.
Do you have any questions for Charlie?
Okay.
Very interesting presentation,
Okay.
Charlie. Thank you very much for that work. I just wonder if you could reflect on the carbon improvement of going for that, for those foundation solutions, and also just the other dimension I'm thinking about is climate adaptation, as to whether the changing climate puts different pressures on foundations that these designs might give further advantage. So,
So on the first question with the sort of carbon comparison, that is something that sort of once we've optimized the foundation, it's something we can look at. But with a lot of these models, it's quite difficult to capture the. As you saw from some of the pictures, this infrastructure is in sort of mountainous terrain, and a lot of the models are developed for sort of urban environments, sort of transportation costs, and the emissions involved in that. So it's slightly more difficult to sort of get a fair comparison. And
I was thinking more on the avoidance of concrete, the actual emissions from that sector.
Okay.
And avoiding that, I would have thought I'm not sure how the comparison between the steel content and the concrete, but that was more the material change.
No, that is something sort of like in future. It would be good to have that comparison. And on the second question was
climate adaptation.
Okay.
Climate adaptation. So with more flooding potentially, or different climatic conditions, any advantages of the approaches?
To be honest, I haven't thought about that, but I guess no, I haven't thought about that. There's something to consider, but yeah, I haven't thought of it.
Okay, thank you very much.
All right, thanks. Yeah, no, I had. So my question was, does would this kind of foundation design lend itself to similar types of transmission pylons that we see, but just with a different foundation, or would there be kind of different economies of scale which might lend itself to kind of a whole different architecture, I guess?
So the industry sponsor SSEN, they've recently developed a sort of monopile tower, which is sort of a singular steel tower. The foundations particularly the helical power groups could also be used for that. So it would be more of a case of scaling up according to the structure loadings. Once you've understood the basic performance and the mechanisms which form, it would just be a case of scaling up according to the structure loadings.
Great, thanks. Any other questions? All right, fantastic. All right, in that case, we'll move to Liang Min from University of Glasgow, who will talk about semi-definite programming for power-to-gas systems.
Okay, good afternoon, ladies and gentlemen, and thank you, Thomas, for introducing me. So, my name is Liang Min. I'm a second-year PhD student from University of Glasgow, and today my topic is the work I have done in this June to this August, I think. So, my topic today is operational coordination of electricity and natural gas network consider power to gas based on the symmetrical semi-definite programming. My supervisor is Dr. Jing Yang, and also this worker this research have co-works of Dr. Chengwei Lo and also Dr. James Yu. And I'm funded by my school, my colleague, and also ETP, and also the Scottish Power Energy Network. So nowadays, we have the problem we need to facing is the environmental issues, energy crisis, and what we want is the UK Net Zero 2050. And so there is increased installation of renewable energy generations, and also there is increasing demand of energy storage. And what we want is maximizing and minimizing. What we want to maximizing is the integration of large-scale renewable energy generations, and what we want to minimizing is the total operational cost and, of course, the overall carbon emissions, money and the carbon. So our solution is that we want to use the power to gas device to convert the power to the natural gas, and then use the electricity and the natural gas network to form a multi-energy systems. And what we want is we can serve the power to gas as a actual large capacity controllable loads to convert the renewable energy generations to the natural gas, and it can be stored in the natural gas pipelines. And so we will utilize the dynamics of the natural gas pipelines as energy storage for the power grids. So what we want is the multi-energy system modeling. Look at that. This one is a very brief description. And so for the power system part, what we have is a three-phase unbalanced distribution network, and we have an assumption is that the upstream power is from coal-fired power plants, although there is fewer coal-powered power plants in the UK, but it's our assumption, and that is what we want to improve. And also there is integration of wind power generations, and of course electricity demand. And for the natural gas network, we have is a steady state natural gas flows modeling, and there is a dynamics of gas storage in the pipelines. I will show you how the pipeline works in dynamic of the storage. And the coupling components is the power to gas device and the gas-fired power plants. And what we want to achieve is bidirectional energy flows from the power system to natural gas. So the power to natural gas, power to gas actually is power to natural gas, and also from the natural gas network to power system is the gas-fired power plants. And thanks for the gas-fired power plants have a very fast response, so it will contribute to our energy flow from the natural gas to the power system. So about case study, the modeling of my case study, look at this one. we have IEEE 123 node test feeder systems as our power distribution network. We have 6 node natural gas network, and also in the power systems, I have 6 wind power generation farms. Each one is about 600 kilowatt. And also we have 2 gas-fired power plants link the natural gas network to the power system, and also, of course, we have 1 power to gas device, which is linked the power system to the natural gas network. And the profile of electric loads in the power system, the gas load in the natural gas network, and the wind power generation profiles. Look at this one. We have high demand of electric loads in the daytime, and however, in the evening time, the wind power is high. So there is a huge gap between the wind power and the electric load during the evening. And this is the energy we want to storage and use in the daytime. Let's see what we can do it. In order to verify our method, we have 3 scenarios. First one is optimal optimizations, but without any link between these 2 systems. Number 2 is operational coordination only with gas-fired plants. Number 3 is with both the power to gas and the gas-fired power plants. So here is some basic results. First, what we want to maximizing is the wind power accommodation. So here is the curtailment. The curtailed wind power, it can be reduced almost 94% of the curtailed wind power. And for the cost and for the carbon emission, there is also we achieve some significant reductions. 10%, 21%, and 25%, almost 26%, and 33%. So here are some figures. First is about the electric power analyzed. Scenario 1, the black column means the power from the coal-fired plants, and the blue column is the wind power. And for the scenario 2, we have many energy from the gas-fired power plants. And in the scenario 3, you can see in the evening time there is obviously increased wind power generation because the operational of the power to gas. So the P2G is used as the controllable loads to observe the energy from the wind power, and in the daytime, the gas-fired plants can use this natural gas to generate the electricity. And also from this picture, this one is about the scenario number 2. What we have is the 2 gas well, and also there is the black line means refer to the gas-fired plant's output, and the blue line is the gas load. Compare these 2 figures, the difference is here. It's the green line and the output of the gas well, because in the scenario 3, the operational of the P2G, the output of the gas well is largely reduced. And also, this figure shows how the dynamic of pipeline works. The green area is when the pipeline is charged, there's increasing storage mass of natural gas in the pipeline. And the red part is when the natural gas is discharged. Charge, discharge, charge. It have 2 times of charge and 1 times of discharge is because I also have constraints, which is that the storage amount of natural gas is same at the time 0 and the time 24. So it will be a fair comparison. So yes, just like a very large capacity of batteries, you charge in the evening and you discharge in the daytime, load peak shaving. But now the energy storage becomes the natural gas in the pipeline. And the last figure is another show of how the P2G can contribute to the accommodate of wind power generation. The red column represents the wind output in scenario 1. The blue column means the wind power output in scenario 2. The black column is the wind power generation in the scenario 3. And the red line is the scheduled wind power. Actually, it's the maximum output of the wind power, and the gray area is the electric load. Yeah, very obvious improve of scenario 3 with the power to gas compared to another two. And also one thing you can note is that at the last hour 23 and 24, there is also some curtailed wind power. That is because what I mentioned before is that the gas storage at the beginning and at the end will have the same value, same number, same value. So when it's here, we do not need any more natural gas, so it will stop to convert the electricity to the natural gas. But if I increase the capacity of our pipeline, I think it should be maximally accommodation of all the wind power generation. So here come to our solution. Of course, this work is not finished, so it is preliminary conclusion. The conclusion is that this method is very effective in reduce the cost of operational cost, increasing the minimum the curtailment of wind power and the minimum the emission of carbon. And what we believe is that is the power to gas can release the system flexibility by converting excess electricity into natural gas injected in the pipelines. And the power to gas consumes the stabilized wind power curtailed by our power system due to its limits, capacity limits, to increase the economic and the carbon footprint of the entire systems. Okay, thank you for listening. Questions, please.
So thank you for your presentation. I also like the idea that you can use other methods of energy storage other than batteries. So that's a new way to see how you can convert electrical energy to gas. But my first question is, how do you do that? Is it that you power the pumps that extract gas from the ground, or how does the conversion from electricity to gas happens? And the second question also, did you consider the capacity of the pipes? So I see that you in the pipelines you store the gas in the pipelines. So what if did you consider that if the pipelines have a maximum pressure or capacity that you cannot pump any more gas into them? So that's
okay. You have actually two questions. So first question is about how the working of power to gas. Actually, there is two process form the power to gas. The first process is to use the electricity to produce the hydrogen, and the second process is to use the hydrogen to have some reaction with the carbon dioxide, and then you can make natural gas. That is how it works. And in the second process, you will observe the carbon from the air, or you can have some stored carbons. So it is another way to reduce the carbon. And for your second questions, my answer is yes. In my model, I not only have the steady state natural gas flow, but also I have the pressure for the loads of natural gas network. As you say, if the value hit the maximum point, it will stop converting the electricity to natural gas, because actually it is safety issues. You cannot let the pipeline be overload and overload. Does that make sense? Yeah. Thank you.
All right, fantastic. Yeah, so I have two questions as well. So the first question is kind of more general, which is, I guess, the
the sort of interest in natural gas plus electricity system versus, say, hydrogen gas plus electricity system, right? That's I'm sure you get that question all the time. And sort of whether this natural gas system actually is a competitor for a future, net zero system, I guess, or is it just an interim stage? The other question is on semi-definite programming. I guess I think you didn't go into too much of the details, right, of the sort of optimization, but I guess the semi-definite programming lets you deal with some of the non-convexities with electricity constraints. Yes. Does it also have benefits for, is it specifically suited as well for modeling non-linearities in the gas side, or what's the kind of motivation for semi-definite programming?
Okay, so for your first question is that I think because actually everyone want to know what's the real network future it is. But what I believe is that we have had a very mature natural gas systems. So why not we utilize it? Even it's just for 10 years, 20 years, we can utilize it for low carbon emissions. And the second is that because nowadays hydrogen become more and more used and more be more attracted by many people, hydrogen cars. What I know is that the British gas have injected the hydrogen into the natural gas pipeline, but there is limits. I think the limit is 20% or 15%. So even in the future, the natural gas network become the hydrogen gas network. This method can also be used. Just power to natural gas become power to hydrogen. Okay, this is the answer of the first question. So for your second question, actually, before this research, my research is use the semi-definite programming in the power distribution network, only power systems. And then when we move to the multi-energy network, and then I turn to the constraints of the natural gas network, I think this optimization algorithm can also be used as the natural gas network. And as you say, it can convert the non-linear, non-convex model to the linear convex model. And also, it can decouple the three-phase systems using the symmetrical components, and also to maintain the power flow, the voltage, the currents as the real power network it is. And also in the natural gas network, you can have the power flow speed, the power capacity storage. You can have the load pressure of natural gas as you want. So you can have everything you look like. That is, I think, why I use this optimization algorithm. Thank you.
Any other last questions? All right. Well, thanks. Thanks very much.